So we're doing the graphical method for this problem with 20% boron 10, 80% boron 11. What we think, if it's 50-50, what is it? What's the average? 50-50 would be 10.5, right? It's an 80-20. And so it should be, what? 10.8. 10.8 should be the average. What is it? Let's see what the average is. Yeah, if you look at the periodic table, the average is 10.811. So we got it. We could have done it more precise, you know. The way we could have done a more precise graphical method is this mass is not 10. This mass is actually 10.013, and then this mass is not really 11. It's 11.0093. We plug in those masses, we figure out the slope, and then we calculate y equals mx plus b. Oftentimes we do get this into mathematical form. So what we do is reduce the graph into an equation. Y is the mass, the average mass, so we'll call it the atomic mass, and m is just the slope. X is the percent boron 11. And so this would be the slope times the percent boron 11 plus the intercept. The intercept would be whatever, 10.0, whatever that is. And so this just gives us another way of solving the problem. Of course, we could use the equation. That's what the book uses. They use the equation. And so first they get the decimal abundance times the isotopic mass for isotope 1, and then they get the decimal abundance for isotope 2 times the isotopic mass, and then just add those together. And so they're using the equation. All right, any questions on this stuff? And we're going to move on here to this. So far we know, the composition of atoms. We know structure part 1. There's got to be more to structure than the nuclear atom model, right? Because some of the properties just don't correlate. We know the concept of average atomic mass. And so can we correlate the average atomic mass with some of the properties? And people have tried to do that, and they haven't been able to do that. And so we're looking for correlations. And so what's needed is a whole bunch of observations. And who took observations is this. This happened before. Or around, I don't know, Mendeleev, I think, preceded Dalton. And so before this whole notion of atoms was widely accepted, Mendeleev and Meyer were looking at arranging elements based on their properties. And they found that certain properties repeat at regular intervals. And the arrangements were not perfect, but there are errors. Well, there are errors in the masses, and how much they weigh. And they arranged things based on the atomic mass, the average atomic mass, which didn't correlate very well. So they rearranged the order. But did they know about protons? No, they just numbered the elements. So this is element number 1, element number 2, element number 3. In fact, you can see that here at the beginning of this chapter. We don't have the figures. At the beginning of the chapter, we have a nice figure showing the numbering of the elements. And so this is the arrangement they got. Well, this is the modern day periodic table. If you look at Mendeleev's periodic table, it's somewhat similar to this, where he grouped things. He grouped things like certain elements behave similarly, so he called these families of elements. So, for example, carbon, silicon, germanium. Actually, germanium wasn't known at the time of Mendeleev. Carbon and silicon were known, and then he just called this something that was empty. And he said there should be an element which has about this mass, and certain properties. He called it like tetrasilicon or tetracasilicon or something like that. It turned out they eventually discovered it. Whoever discovered it named it germanium. So that was it. And so there are certain holes in the periodic table because certain elements haven't been discovered yet, but they all fit this. And so this is a pattern of properties. And so the pattern properties are, we have families. So this is the what we call the alkali metal family, the alkaline earths. These are the transition metals. This is the main group, the boron family, the carbon family, the nitrogen family. Nitrogens are sometimes called nicogens. In the oxygen family, sometimes it's called the chalcogens. And the fluorine family is often called the halogens. The nicogens and the chalcogens aren't that common, but the halogens are, so you should know halogens. And what we call the noble gases, these used to be called the inert gases because they're so unreactive. And now they're called the noble gases. We have the rare earth elements, the transition elements, these groups here, the rare earth. Well, anyway, what happens is as we go across a road, the properties vary. The properties vary from very metallic, like cesium is quite metallic. Metals share certain characteristics. Metals are malleable, they have luster, they conduct electricity and heat very well. And so what we do is we slowly transition from metallic properties. Well, gold's pretty metallic, mercury's pretty metallic, thallium, lead, bismuth. Bismuth is becoming less metallic. Polonium, actinium, unfortunately, these are radioactive, actinium, radon, these are non-metallic. And so we transition from metallic to non-metallic as we go across the periodic table. And so this is the arrangement in terms of properties and physical characteristics of these arranged here. And so we see a pattern there. And so we see a pattern here, the pattern called the periodic table. Now we have to come up with some kind of hypothesis. People have been trying to come up with hypotheses. Like Mendeleev, they tried to do it based on the average mass, so the black numbers here, because they weren't working with individual particles. But they didn't correlate. Then we tried to correlate with the red number. Actually, we tried to correlate with the red number, the atomic size. So we tried to correlate atomic size with the red number, 1 proton, 2 protons. But when we got to 3 protons, it behaved differently. So it did behave differently, so it didn't go 1, 2, 3, and went 1, 2, then down to 3. So there's something different about it, right? And so in other words, we got all these properties, we need to correlate them with something regarding composition or something regarding structure. And so what can we correlate it with right now? Can you see? Well, not really, so let's just take a look at the properties right now. If we look at the properties of this, we have the periods. The periods are the horizontal rows. Okay, and there are, like, how many rows are there? 1, 2, 3, 4, 5, 6, 7. There's actually 7 rows. This is not the 8th row, this is not the 9th row. Because what happens is the row gets quite long. And what they had to do was, to prevent the periodic table from growing too long, they had to do this. This row is very long. In fact, this isn't the true length of this row. The true length of this row is it goes, take a look at the numbers, 55, 56, 57. Where's 58? Down here. So we got to insert 58 here, go all the way through 71, then we're back to 72, 73 on. So this row is exceptionally long, as is this row, exceptionally long, which makes for an awkward looking periodic table if you have 2 super long rows on the bottom. So what they did was they cut it out and put it down here instead. All right, so what we're doing here is we're just going to look at some of the properties and maybe try to understand some of the properties. Now, the chemical families are the columns, vertical columns. Elements with similar properties placed in vertical columns, identified by 2 rows of numbers across the top of the table. And so there are different ways we can identify these, depending on the periodic table. And there's certain kind of codes for this. And so we have the numbers here, 1, 2, 3, 4, 5, etc., all the way up to 18 over here. And then we have another code, 1A, 2A, 3B, 4B, 5B. We have the 8Bs, the 1B, 2B. These are based on certain chemical characteristics or chemical properties of these elements. And that's why we have this alternate numbering system here. The alternate numbering system can help you. So, for example, if you need to memorize the charge on zinc, you know what the charge on zinc is? Well, the zinc ion only has one charge, it's +2. So it's 2e. Silver only has one charge, it's 1. And so these are called the pseudo. And so we have the regular, the 1a, and the 2a, and the pseudo 1a. But we call it 1b instead, and 2b here. We'll talk more about these as we go along. And so there's certain properties that we pick up little by little. We have the main group elements, 1, 2, and 13 through 18. The group A. The B's are called the transition metals. Those are elements in the B groups. Then we have the metals. The metals are on the left, the non-metals are on the right. And then we have a dividing line. The dividing line is a stair-step line. Any element on the dividing line is called a metalloid. And so let's take a look at that here. So, we're becoming less and less metallic. So let's pick this one. That way we don't have to deal with these radioactive. Take a look. One of the reasons I can tell immediately that this is radioactive is because of this. Take a look at the average atomic mass. Do you see it's in parentheses? Yeah, it's not so easy to measure these things. All these ones in parentheses are radioactive. Sure, uranium they did lots of measurements, so this is fairly precise, but some of these are very short-lived. They don't live very long. So we go over here, let's go across here, metal, metal, metal. We go, tin is metal. Antimony, would you consider antimony a metal? Not really. It's borderline. Tellurium, no, that's non-metal. And so this is the stair step we're talking about. When we go from aluminum, which is metal, to silicon, silicon is a semiconductor. When we go from germanium, which is a semiconductor, arsenic, which is also a semiconductor, antimony is a semiconductor, tellurium is non-conductor. When we do this, on the line here, this is kind of the dividing line. On the left are the metals, on the right are the non-metals. Non-metals don't share the properties of metals. Non-metals don't conduct electricity very well, etc. Non-metals have more varied properties than metals. Metals all share similar properties. Non-metals have widely varying properties. So the non-metals we don't really group into one single characteristic type. But anyway, anything in this transition region is called a metalloid, or a semi-metal. That transition region. And so the metalloids are the elements that border the stair-step line. They have the properties of both metals and non-metals. Boron, silicon, germanium, arsenic, antimony, tellurium are a common metalloid. List the atomic number, okay, active exercise. List the atomic number, chemical symbol, and atomic mass of the third period element in group 6A, 16. So third period. Let's talk about the jargon here. The first period is the first row. So first period, second period, third period. Third period in 6A. What element is that? Sulfur. What's its atomic number? 16. And its mass, the average atomic mass? 32.06. Let's see if we get it right. Sulfur. 16, symbol F. It's a main group element, non-metal, correct? Yeah. It's in the non-metal region. I didn't do that. This is right to the right of the stair-step line. See here. Sulfur is clearly a non-metal. Phosphorus is clearly, but silicon is on the border. Phosphorus is the corner. Phosphorus is distinctly characterized as non-metal. All right, study figure 519 briefly. Look at the periodic table of figure 519b. Try to name as many elements as possible. This is an exercise in memorization. The more you look at it. Here the table of common elements. This is something similar. This table of common elements, you should know all these. Just go down. You should have all these memorized. eventually, when we get to the nomenclature. You still have time. Here's a table of common elements. There. All right, that's it for chapter 5. Now, you know, since we did finish chapter 5, you need more time to study it.
Yep.
So maybe what we'll do is we'll cover the material up through yesterday and today's material not, or cover the material through Monday, because that means, you know, your next test will have more material or less material based on it. So it depends on what you want to do. Up through yesterday's is probably fine, or through Monday. Yesterday? Yeah, so this average atomic mass won't be on the test. Although some people find the average atomic mass calculations to be fairly straightforward. You don't have to use this graphical method that I use to determine it. Now, I did say that there's going to be quite a bit of memorization. So let's take a look at chapter 6. Here's where some memorization starts. So, you know, it wouldn't be a bad idea over the weekend to get started on this memorization. Nomenclature just means naming these things and figuring out the formulas. So chemical nomenclature. Nomenclature is a bit of a pain because you got to learn how to name all this, and that just involves memorization. Sometimes we can see patterns. These patterns can help us decrease the amount of memorization. Here are the learning objectives for chapter 6. All right, so some of this stuff we've already talked about. You know, some elements, well, the majority of elements exist as single atom particles. Is that true? Single atom particles. In a way, yes. In a way, no. The majority of the elements occur as lattices. And the lattices have no beginning and no fixed, well, they have a beginning. They don't have a fixed ending. You know, lattices can keep going in all directions. And so something like gold, you know, gold consists of atoms arranged in a lattice. The lattice can grow bigger and bigger and bigger. And so it depends. Whereas helium does occur as single atom particles. You know, atoms of helium in a gas. So there's no problem there. Whereas lithium occurs in a metal lattice. If you look at lithium, all the atoms are packed together in a lattice network structure. So helium and lithium are two totally different structures to me, although they're referring them to single atom particles. But we do have diatomic molecules. Diatomic molecules exist as distinct units, 2 atom units. These are the 7 diatomics. Everybody should have these memorized. You know, hydrogen, when somebody talks about hydrogen, they're talking about each 2. When somebody's talking about oxygen, they're typically talking about O2. Okay, that's what we automatically assume, but it's not always this way. So we need to clue in on certain subtleties of the question if we're talking about O or O2, atomic oxygen or diatomic oxygen. Okay, so can we write the formula for chlorine? Self-2. Argon. AR. Right. And so chlorine occurs as diatomic gas. So it's got a gas molecule of chlorine. Argon occurs as single atom gas. Okay. Bromine is actually a liquid. And so bromine's a liquid, and so we're going to have diatomic molecules packed together in a liquid. And so all these diatomic molecules are going to be kind of stuck to one another. But there's still translational motions, so they can move. So bromine would be like that. Br2. Krypton is a single atom gas, like argon. You know, so this would be chlorine, would be argon. This would be bromine. Okay, now the chlorine we call Cl2G. Argon we call ArG. Bromine we don't call. Yeah, it's a liquid. So what we use L. Liquid. And finally, krypton occurs as single atoms in the gas phase. So this would be krypton G. What if we had gold? Gold, well, we don't know exactly the ending. So there could be a million, billion, trillion. I don't know how many gold atoms we're going to have, but a whole bunch in a piece of gold. And they're just packed together in a lattice. So this would be solid. Got that. Okay, we talked about this here. This is a color picture here. Hydrogen's an unusual one. Hydrogen shares both metallic and non-metallic properties. And so,
Considered a metal.
sodium's a metal. Why is it considered a metal, or what was the question?
We know why it's considered a metal. Because it's a crystalline structure that includes not.
Yeah, well, gold is a crystalline structure too, and gold's considered. Have you seen what sodium looks like? Let me show you a sodium metal. Here. Wikipedia. This is what sodium looks like. Sodium conducts electricity very well in all directions. It has a luster. In fact, this looks a little bit oxidized. When you cut sodium's soft metal because of the structure, the way the structure is and the size of the atom. But you can easily cut sodium with a steel knife. If you cut sodium with a steel knife, you get a fresh surface. It has a very silver-like luster to it. And so it has all the properties of a metal. Metals are defined as being malleable. Sodium is malleable. Ductile. You can stretch it into wire. Sodium is not that ductile, but a little bit. It has good electrical conductivity. Has good thermal conductivity. And so what is a metal? A metal is anything that fits that definition. And so we define the metal as having these properties. So anything that has those properties will be considered a metal. Sodium has those properties, so it's considered a metal. That's what we call it. Just based on properties, we would look at the structure too. The structure plays an important role. All right, so let's continue on here. Hydrogen's very interesting because hydrogen you think is non-metal, and is H2 gas, like non-metal. Does hydrogen conduct electricity? Does hydrogen have a luster? And the situation is, if you had solid hydrogen under pressure, it conducts electricity. Can you believe it? Like a metal. And so it's weird. Hydrogen's weird. It has properties of both metal and non-metal. So if you look at our periodic table is kind of funny. Our periodic table has hydrogen here, the alkaline metal family, and then it has hydrogen here in the non-metal family, which is a halogen family. That's because hydrogen has properties that are similar to the halogens, and hydrogen has properties similar to the alkaline metal. And so therefore, it's grouped into two different families.
For oxygen, I know that once you turn it into liquid, it's magnetic.
Oxygen is magnetic even before you convert it into a liquid.
Oh.
Yeah. It's just easy to see it's magnetic when it's in liquid form. Magnetic properties we really haven't talked about yet, but maybe we'll talk about those. So it's not that hard to liquefy oxygen. These are have one with reflection. Well, here you can capture the liquid oxygen in the magnetic field. So oxygen is magnetic, so it's going to be attracted to magnets. So that's liquid oxygen there. Liquid oxygen is very dangerous stuff because liquid oxygen is powerful, what we call an oxidizer. And so the type of magnetism that oxygen displays is paramagnetism. I don't know what's wrong with the audio. Sometimes that happens. Somebody plays with
Bottom right corner.
What's that?
Bottom right corner.
Oh, there it is.
And pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet. And then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
This is liquid nitrogen. No, they're going to make some liquid oxygen. So this is liquid nitrogen, and they're passing oxygen gas through liquid nitrogen and cooling it. When gases expand, it cools according to one of the laws. Here, they can condense liquid oxygen over there. Liquid nitrogen is about 95. You have to get it colder than that. The crystals, the ice crystals, are just forming from humidity, moisture and air. Wow, they got a lot of liquid oxygen. That's called a dewar. It's a vacuum flask. Is this liquid nitrogen? Liquid nitrogen is not magnetic. Liquid oxygen is magnetic. It evaporates pretty fast though, vaporizes, boils off.
Is the liquid oxygen really cold?
It's really cold. Colder than liquid nitrogen. Liquid oxygen is colder than liquid nitrogen. Not much, just a little bit colder. You got to watch out because lots of explosions have happened due to unintentional formation of liquid oxygen. A lot of people use liquid nitrogen for cryogenic purposes and accidentally make liquid oxygen, resulting in an explosion when it comes into contact with liquid oxygen coming into contact with combustibles is dangerous. How cold is liquid oxygen? Well, all we need is to know the boiling point of oxygen. So the boiling point is 90.19 Kelvin. It's the boiling point of oxygen. Nitrogen is a little bit higher. Nitrogen's boiling point. Okay, so they did that in Kelvin, and this is in Celsius. So add 273 to that, and then you get nitrogen. Or subtract 273 from the other, when you get oxygens. So let's see. Well, let me talk. Since we're running out of time, I want to show you something to start memorizing. And you need to know the names and formulas for certain ions, and some of these ions are not so easy to remember, but there's a certain pattern that helps you remember them. Just a heads up.
Our time is up.
Time's up. Is time up? Oh.
Yeah, today's another 12
Well, we're at 12:20 today? Oh, shoot. All right.